the basic condition that you have when you have oscillatory motion is that the object is repetitive. The motion repeats itself, correct? The motion repeats itself, so there is a number associated with that, which is called a period. That tells you after how much time you're going to have the object go back to the same original place where it was, doing exactly the same thing that it was doing before. As you know, you've probably played with this or you saw it. If you take a block, attach it to a spring, you pull it, you let it go, the motion of the block is oscillatory. It goes one way and it goes back and it goes the other way and comes back and so on. And it keeps oscillating about a special point, which is called the equilibrium point. If there is no friction, the object keeps moving forever and ever in the same way. If you started it at a distance a from the equilibrium position, and if this is attached to a spring, as I said, no friction anywhere, then the block is going to go all the way to the other side, and it's going to stop at a distance a from the equilibrium point. If you started at a from the equilibrium point, then it ends at a from the equilibrium point. Not ends, but it goes all the way to the a, then it bounces back. On its way back, it's going to reach exactly the same point A, then it's going to stop. The spring is going to pull it back, so it starts moving towards the equilibrium point. When it reaches the equilibrium point, the force is going to be 0 because the spring is not stretched anymore, but that doesn't mean that the block is going to stop, right? The object has picked up momentum, so it passes, it overshoots the equilibrium point because it's going with some momentum. So it goes to the other side, then now it's compressing the spring is slowing it down, until it takes all of its momentum away, right? The energy gets stored in the spring in form of elastic potential energy, but the block stops, but it's not going to stay there because the spring is compressed and is pushing it, constantly pushing it in the opposite direction, okay? So that's the mechanics of this kind of motion, right? As I said, there's going to be an amount of time, t, this is not torque anymore, so you have to be aware of that we use the same letters in physics because there's not that many letters to choose from, even when you add the Greek alphabet. So this is going to be the period. And you have to look at the context of the problem to figure out that this is not torque, this is period now. Okay, sorry about that, but like I said, ran out of letters. So that's the period, and it is the amount of time it's the amount of time that it's going to take the object to come back to the original place, whatever your origin is, it's up to you. But when it comes back to that place and it's moving with the same velocity, that means same direction, right? Not just magnitude, but also direction. Then you call that a period. So you can start to count the period. You can start the object here at a distance a from the equilibrium point. So it goes this way, right? It comes back and it stops. Right? So that is one period. It came back to your initial location and it came back with the same velocity, which is 0. Correct? But you could have started also counting t equals 0, might have been here when the object was passing the equilibrium point. You start your clock and you say, what's the period here? How do I count the period? So the block passes the equilibrium point, it moves to the other side, stops, and it comes back. Then you say, oh, I came back to the original point. That's my period. No, it's not. because it's not moving with the same velocity. It's back to the equilibrium, but now it's on its way to the right. When you started your stopwatch, the object was going to the left, passing the equilibrium point. So that is not the period. That is half of the period. All right? So keep an eye open for that. So you can start at any time. You can start your t equals 0 when the object was somewhere between this and that. So the block is going to go this way. It's going to pass the same point, not moving with the same velocity. You still have to let it go. And then when it finally comes back, it's moving to the left. That is your period. And then there is a quantity associated with period, which is the inverse of it. Frequency f, that's the symbol that we use normally, and it's defined as the inverse of the period. What this quantity is telling you is the number of oscillations, complete oscillations, per unit time. So suppose that you have some object that is oscillating back and forth very fast, and you wonder how many times, how many complete oscillations that this object do in 1 second, right? So you start, count how many, stop 1 second later. How many did you count? That number is going to be the frequency. So if you counted 3 complete oscillations in 1 second, maybe that's the frequency at which I'm moving my hand right now. In 1 second, maybe 3. So the frequency of my hand at this moment in time is 3 hertz, 3 oscillations per second. The units of this thing hertz, which is the same as oscillations per second. So when you tune a radio station and you tune it at 103.5 megahertz, that means that the signal that is bringing this radio station music to your stereo, that signal is oscillating with 103.5 megahertz, millions of hertz per second. Every second it oscillates 103.5 million times. Okay, so that's what. So for very fast motion, you probably prefer to use frequency, because otherwise, when you talk about the period of the electromagnetic signal bringing the that is received by the stereo, you're talking about, you know, an amount of time that is 1 over 103.5 million hertz. That's less than a millionth of a second. So if you don't want to carry that or talk about such a small amount of time, then frequency is just as good, right? Okay, so they're the inverse of each other.
The inexorable law in mechanics is F equals m times a, the second derivative of x. In simple harmonic motion, force comes from the displacement x itself. F equals minus kx. Together, these two equations give the differential equation that describes simple harmonic motion.
That differential equation refers not only to a mass on a spring, but to any physical system that, when disturbed, is restored toward equilibrium with a force proportional to the disturbance. For example, the pressure of the air in an organ pipe, or the angle of a pendulum, the bending of a tuning fork, or the rotation of a clock movement. These systems and many others undergo harmonic oscillations. These oscillations can be too fast to see, at least under normal circumstances, or too slow to wait for. Or they can be any other frequency, high or low. No matter the frequency, however, they can all be described by the same differential equation. The differential equation is solved by the time-honored technique of guessing. A long time ago, someone guessed that the solution may be a sine function. It was an educated guess, because the motion of a mass oscillating on a spring resembles the motion of the shadow of a particle moving in uniform circular motion. So the idea of guessing a sine function seemed quite natural. In this case, a sine function with amplitude A and angular frequency omega. But if that's x, is its second derivative equal to minus k over m times x? The answer is yes, if omega is chosen correctly.
For the mass on a spring, the angular frequency is equal to the square root of k over m. The stiffer the spring, the higher the frequency. The greater the mass, the lower the frequency. But whatever the frequency, it depends on the mechanical properties of the oscillator, such as the mass and the spring constant. The time needed to make a complete cycle does not depend on how big the swings are, represented by A in the equation for x.
So even as the oscillations die down, harmonic oscillators continue to keep perfect time. The frequency is measured in radians per second. There are 2 pi radians in each complete cycle. Likewise, in the great clock in the sky, each cycle is divided into radians, as if the universe were an enormous circle. To an extent, it is. The natures of uniform circular motion and simple harmonic motion are closely related. Each clock, in its attempt to duplicate the cycles of nature, is a mere shadow of the cosmic clock. Just as uniform circular motion and simple harmonic motion shape up much the same in nature, the potential energy of harmonic motion can be visualized as a curve shaped like a bowl. Why this shape? Because of the force law and the definition of potential energy. The ball starts out with some potential energy. As it rolls toward the bottom, the potential energy changes to kinetic energy. As it rolls up the other side, the kinetic energy changes back into potential energy. Over time, there's a continual interchange between kinetic and potential energy. But even though both the potential energy and kinetic energy are always changing, the total energy is always constant. When any harmonic oscillator is disturbed, the disturbance produces a force that pushes it back to where it was. There, the force is zero, but inertia keeps it going until the reverse force stops it and pushes it back once again. This is the essence of harmonic motion. A simple harmonic oscillator. If it were really simple, it would go on forever. A perpetual motion machine.
All right. So let's start by talking about the main points that that video makes. First one is we're talking about a spring, right, connected to a mass. The mass has been displaced at some time before from the equilibrium position, and it exhibits this periodic oscillatory motion, right? It goes to the left and back to the right and back to the left and so on continuously. Now, to describe this motion, we can look at what does the force depend on, the force of the spring, what does it depend on? And we use Newton's second law to say that the force is equal to the mass times the acceleration, right? So the equation that we're talking about, that we're going to end up writing, is starting from Newton's second law. We say that the only force acting on this mass is the force of the spring. So that force is going to be minus kx. I'm going to use the origin in all of these oscillations problems. We're going to use the origin of the x-axis to be at the equilibrium point. So I don't have to worry about writing the delta x, right? It's always going to be measured with respect to the equilibrium point. So, because that delta x with the differential kind of makes equations a little messy, so we're just going to use x. So the force, which is the force of the spring, is minus kx, and that should be equal to the mass of the block times the acceleration of the block. Acceleration, and we're going to have to use differentials notation at least in this part of the material. Acceleration, as you remember, is the second derivative of the position, right? Velocity is the first derivative. Acceleration is the derivative of the velocity with respect to time, which means is the second derivative of the position. Okay, so the equation that we have to describe the motion of this mass is this equation, where x is measured from the equilibrium, is the position of the block as measured from the equilibrium point. Now you might wonder how boring this stuff that we cover in physics, you know, a mass attached to a spring. When have you ever played with that, or when have you ever seen any application of that, you know, in your life? Why do we care about blocks and spring connected to springs and see how they move, right? You might wonder that. The reason was explained in the video. Let's see if you got that part. Why do we care about this? Anybody? There's got to be something important about it. Go for it. The what?
Like the idea of like oscillation used for infrared spectroscopy to figure out like what compounds.
So you're talking about oscillations happening in molecules, okay? All right. So he's saying that this might be important because we're talking about oscillations, and there is oscillations in chemistry, in molecules, okay? What other possible examples are there that you can think of? Yeah. Mm-hmm. Okay, sure. It describes the motion of a pendulum, for example. If you are interested in finding out how does the pendulum move, then this will be useful, as we're going to hopefully do at the end of the class. But who cares about pendulums anyway, right? Yeah? Oh, I thought you were going to say something. Any other example? Yeah? It's an oscillator. Correct. That's right. So what I'm getting at is that even though we're talking about a very highly simplified situation where we have a block and a big spring, right, and you almost never see that working in real life or any application, this stuff is very universal. The equation, this equation, is probably one of the most famous equations in physics. It's the simple harmonic oscillator equation. And it describes the oscillatory motion of pretty much anything that you can think of. There are examples of things that move in a periodic oscillatory way that are not described exactly by this equation, but those are the exception. The rule is that whenever in your life you see something that is going back and forth, that hasn't, first of all, if you see something that has a resting position, and that if you disturb it, it goes back and forth, that object that you're looking at, the motion of that object will be described by this equation to a very high degree of precision. Okay? Anything you can think of. If you think of a building, for example, oscillating because of an earthquake, this will describe that oscillation. If you think of the current oscillating in a circuit, for example, this will describe how that current changes with time. If you think of the motion of a pendulum, like I said, pretty much anything you can think of that goes back and forth around a equilibrium position does behave like that. So you can see that that is a very important thing to know about how the universe works, because so many things in the universe work according to that equation. So that's why we're studying that.